All right. This is the binary star problem. It does appear, it has appeared on the AP exam, and it is fair game on the AP exam. Um, but the way that it works, we call it the binary star problem because you basically have um, two bodies orbiting the same center of mass, and they may have different radii. So, for example, here you're going to notice that little m has a larger radius from the center of mass than big M does. Okay. Okay, so now consider mass m is less than but comparable to big M. Both objects now circle a common center of mass. The mass big M makes a circular orbit of radius r about the center of mass, and the mass little m makes a radius r. The total distance between the two objects is d. Okay. Um, Write an equation that relates big M, little m, big R, and little r. So what I'm going to do here is I'm actually just going to use the center of mass equation, right? We remember that for center of mass, right? You take the mass times its distance from the center or from the or its position along the axis or whatever, right? Well, I'm going to do the exact same thing here. I'm going to say that mass big M is a distance big R from the center. So I'm going to do if the center of mass stays right here and doesn't move, right? Then this should actually just be big M times big R equals little m times little r. And it's really important to note, to watch out, because in this case, little r is greater than big R, and that's confusing, right? But the reason why is because the capital letters are paired with each other, and then the lowercase letters are paired with each other. That's why it's like that. Okay. Okay. Um, Now, to get the expression for omega, okay, it wants me to get an expression for omega in terms of big M, little m, d, and fundamental constants. All I can, really what I'm going to do is I'm just going to use the Newton's law of universal gravitation and centripetal force, okay? So I'm going to do g little m, big M over r squared. The distance is actually going to be d, okay? Equals big M, or sorry, little m omega squared times r. Okay. Well, I can actually cancel out my little m's because I'm calculating the force, really, the omega here. Okay. So I can cancel out my little m's. Okay. And I end up getting, this is going to be g big M over d squared equals omega squared times r. Okay. Um, and I should also note here, okay, that so I've got omega squared and r. I actually need to get a new expression for r, okay? And that's actually what I'm going to do right here off to the side really quickly, okay? I started out with this expression up here, okay, which was capital M R equals little m r, okay? And so what I need to do is I want to get what I want to realize is that this d right here is equal to the two r's combined, little r plus big R. Okay? When I combine this, so ultimately what I want to do is I want to get things in terms of d because that's what I'm allowed to have. So in order to get there to be some term of r plus r, what I want to do is what I do to one side I must do to the other. Okay, I'm going to do something of it's like a crossover term. Okay, where I'm going to add on both sides capital M times little r, capital M times little r. And this will actually make it so that I can do some factoring on both sides. Okay. When I factor on the left side, I can factor out capital M, and I end up getting R plus capital R. And then on the right hand side, I can factor out little r and get little m plus big M. Okay. Okay, and then I recognize that this right here is D. Okay. So I can actually express little r in terms of D and everything that I'm allowed to have, right? So that's exactly what I'm going to do. I'm going to turn this into this. This is going to be capital M times D equals R little m plus big M. Okay. And then if I get R by itself, I just got to divide M plus M, and I end up getting R equals um, capital M D over M plus M. Okay. And so I'm going to substitute that right here. Okay. I'm actually just going to make this G M over D squared equals omega squared times M D over M plus capital M. Okay. I'm kind of crunching that in there, but that's okay. Okay. Well, now what I can do is I want to get omega by itself, right? Well, what I can actually do is I've got capital M, capital M. I can cancel those two out, okay? I can divide the D on both sides and then multiply the combined masses, and I end up getting that omega should be equal to um, G little m plus big M over D cubed, okay? And then I can just root both sides, or sorry, this is omega squared. I can root both sides to get that. So I would end up getting that omega is equal to root G little m plus big M over D cubed. Okay. And then what I'm going to do is I can then actually, to get the period of orbit, which again, I'm going a step further in doing this, I can then do root G little m plus big M over D cubed equals 2 pi over T. I flip both sides and then I multiply by 2 pi, and I'll end up getting T equals 2 pi root D cubed over G little m plus big M. Okay. So that's just, I mean, I just went a step further and got this, but really you just had to get the omega equation. Okay. Okay. And the final part here says that show that if big M is way larger than little m, the expression for omega reduces to that of the circular orbit motion or circular orbit equation as shown above. So what I can do is that if this condition is true, if big M is way greater than little m, okay, then I can say that big M plus little m just equals big M, okay? Because if you think about it, right, what if big M is 100 and little m is like 0.001? Well, 100 plus 0.001 is 100.001, which is basically 100, right? That's how we get that. That's how we kind of got that. Well, if this is true, okay, then I'm going to go back to my derivation up here, and I'm going to say that when I do this part right here, MD equals R M plus M, this is just going to be MD, that's what I meant to do, okay, MD, oh, that looks like I wrote parentheses, I didn't, okay, MD, sorry, I'm just trying to make this look really clear here, okay. You know what? Let's just rewrite it, okay? M D equals R big M plus R, okay? Wait, no, plus little m, okay. Now, this part right here is just going to become big M, okay? So this becomes big M D equals big M R. Well, then you have an M on both sides, and you can cancel those out, and you can just see that D is equal to R, right? Well, then when you go back into your omega equation, okay, if I go back into the equation that I wrote for omega earlier, omega equals root G little m plus big M over D cubed. Well, if I make my appropriate substitutions, which is that this is now going to become R, this is now going to become big M, okay, that's all I got to do, okay? I just get omega is equal to root G big M over R cubed. And if you notice that's exactly what we got for the circular orbit example, okay? That's exactly what we got for the circular orbit example. So it's the exact same thing, okay, if big M is way bigger than little m, which you cannot reasonably assume unless it's told to you in the problem, okay? You don't want to make an assumption. You want to be like, oh, well, big M is quite a bit bigger, so we're going to, no, you can't do that, okay? All right, that's binary star problem.